welcome back. In the last lecture, I discussed the fundamental technological difference between a cobot and a traditional industrial robot and how it has advanced over the years. I have discussed the design of the joint actuator, the controller, arm, and the overall system. So, in this lecture, I will discuss the fundamentals of its implementation, that is, the constrained motion task and the distinguishing features of a cobot that we look for when we use a cobot. Let us first have a look at the lead-through programming that we have heard of quite often that a cobot possesses. Is you can take it to any point, you can teach it instead of jogging it to a location and teaching it. So, this is something very innovative that has come with the cobot. Let us have a look at that. So, you see what I am doing, I am taking the robot to different points on a trajectory, okay, and I am teaching those points while I am dragging the robot through manual, through my hand only. So, I am able to drag it. This robot is so soft, it allows me doing that. So, every point I am taking it, I am teaching it, taking it, teaching it. So, I am not required to take it through my teach pendants, I am not jogging it manually. Okay, I can directly take my arm and the arm is quite soft. Okay, once it is completely trained, what I will do, I will just play a repeat button. So, whatever points I have taught, it will quickly follow that. This is one very good feature that is normally there in a cobot, because it is back drivable and it is compliant. It is fully gravity compensated also, so it is very easy doing that. So, this is one of the very good feature which is there in a cobot. Okay. So, let us continue with understanding the constrained motion task. The first one is writing on a board. So, when we write on a board, what all things that goes there? You see, what is happening is the robot is able to write on a board that is placed horizontally on the table. The situation is very much like this. When you have motion axis along the plane, I can move the robot along the plane, okay, and there is a point of contact that is happening somewhere over here. So, what are the constraints which are there? There exists a translational constraint, that is z downward direction. I cannot make the robot go into the board, okay. So, actually it can remain on the board, and there has to be constant normal force that is to be maintained while I do all the writing process, okay. So, the force along z downward direction is only allowed. If you take the force along the vertical upward direction, it will lose its contact and no more writing will happen. So, you have to continuously maintain the normal force against the surface, and because there is almost negligible friction along the surface, you are free to move along x and y directions, okay. So, rotational constraints also there are none. It can rotate about its any of these axes, it can roll, it can pitch, it can rotate about its own axis. So, there is no rotational constraints here, but yes, once it has established its contact using the robot, this orientation change is not very much required. So, the robot may be commanded to write by moving on the xy plane, that is the surface, while maintaining a constant reaction force along the vertical z direction. Essentially, you can produce force only when motion is constrained. A robot which is free to move in the air cannot generate any force at its end effector. Got it? So, in whichever direction out of the 6 directions, 3 for translation, 3 for orientation, whichever is constrained, you can generate force or moment accordingly in that particular direction. So, that is the philosophy here. So, this is how the writing happens when we do it using a robot. So, negligible friction is there along the x and the y direction. Okay. So, the next one is the case of a milling. Okay. So, let me show the video once again here. So, this is a milling operation when a robot is taken to one end of the board, that is, this is the wooden board with a pneumatic drilling machine, and you have a end mill which is fitted there. So, again it tracks the whole of the trajectory, okay, removing the material along xy plane, that is the plane of the plank which is here. You see, it moves throughout the surface and finally it finishes it. So, once it is completed, it takes up the tool. Okay. So, reaching till that point and going back is basically a position control task. So, it is a position control trajectory using a standard robot, but maintaining the contact, doing this work requires some compliance in action. So, that is what is realized here. So, there is translational constraint along z direction, just similar to the board writing process that we discussed in the last slide. Okay. So, you can generate, you need to generate a constant force along the z downward direction, so as to maintain a constant contact. Okay. Once that is established, there is an external loop that allows the further going down to be stopped. Okay. So, once you establish a contact and go certain distance downward, you need not to go further down. So, you stop further going down. So, z direction it is limited. Okay. Now, the x and y direction. So, force guided motion along xy plane is done. External force control loop with the inner position control loop is taken here. Why? Because so you have to command for the position. So, wherever you want to go, you continuously tend to go there by giving position command, but externally it is force limited. So, while doing the machining process, there is a machining force along the xy plane that constrains the motion. You have to continuously check the forces. You cannot apply infinite amount of force to go to the position commanded trajectory. Instead, this is a force which is stopping it to go there, and further with a constant force you keep on moving in particular direction. So, this is known as a force guided motion. Okay. So, external interaction, that is the milling forces, this regulates the speed of the tool along the commanded position or that position trajectory and keeps the trajectory intact. So, the trajectory is not changed, but the speed with which it is moving is regulated by the forces, because you have a external force control loop. So, this operation is little bit different from the board writing process, when we assume there is no frictional forces along the xy plane, that is the plane of the board. Okay. And there is no rotational constraints here, but still we do not prefer doing the roll and pitch or even yaw motion. Yaw motion is anyway redundant, we should not do that, but we also do not do this roll and pitch motion for this robot. Okay. The frictional and the cutting forces are along x and y directions. Okay. Okay. The next one is a peg in a hole task, that is inserting a pellet, which is a cylindrical pellet, inside a hole which is drilled in the surface. Okay. So, how that is done? Let us again look a small video. This is a cobot. It starts from the home position, picks up the pellet in position control mode only, okay, goes vertically above the hole using a vision system, maybe lowers vertically in force sensing mode. Now, it is lowering, but it also monitors the force that is coming in. As soon as it establishes contact, it starts searching the hole, okay, and the pellet is inserted. So, close up of the lowering, contact and the search process. Finally, the insertion process is shown here. Okay. So, this is a KUKA Aiwa robot, which is a cobot. So, in this case, There are two operations. First is the hole search operation, next one is the insertion task. The constraints are different in both the cases. So, when the peg is outside the hole, when it is literally very much off the hole, then you can move it in position mode. When it is on the surface and outside the hole, the robot slides on the surface maintaining a constant reaction force. While it is searching, it does maybe spiral search or some other kind of search, okay, Lissajous search for rectangular subspaces. So, in those cases it searches for the edges and continuously monitors the forces, and finally it finds the hole. Hole searching is a different algorithm altogether. So, as soon as it finds the hole, it simply drops the pellet if it is gravity supported, or it simply does the gravity guided or the force guided insertion process. That is the second phase of it. This case is very much similar to the pen sliding on the board. I assume there is no frictional force again. Okay. Now, the pellet insertion task moves inside the hole. This time there are two constraints. The one which is shown here, it is with peg insertion task, that is inside the hole. Translational constraints are there along the x axis and the y axis. So, those two axes you get the reaction forces if you move little off. Okay. So, the force axis is along x and the y directions, free to move along vertical z direction. As soon as it finds the hole, it is free to move along z direction and it cannot produce any force. Okay. So, the force guided insertion takes place. So, if it gets little bit off, you have to come back, or end effector compliance out of impedance controller takes care of that, and finally you can push it inside the hole, or you can just drop it if it is gravity supported. Rotational constraints along x and y directions exist. You cannot roll, you cannot pitch also as soon as it gets into the hole. Okay. So, the peg is inserted and released upon sensing a drop in vertical forces. How does it know actually? It has reached to the hole. Actually, it continuously senses the z direction force. There is a sharp change in the force value as soon as it gets to the hole, okay, and it drops it or it pushes it in. Okay. Now, the next one, opening or closing a sliding drawer. Drawer can be of many type, but this is a sliding drawer in which this board can get in and out. Okay. So, this is the constraint here. So, you have motion axis, that is along z axis again, and x and the y directions are fully constrained. That means your robot cannot displace along those directions. So, in this case, translational constraints exist along x and y. Translation constraint along z axis, there is none. Okay. So, it is free to move along z direction. So, it can produce forces along x and y direction if at all it is perturbed. Okay. So, this kind of assembly again requires an external force control loop, or in case of a cobot it can be impedance controller. So, it has a quite good amount of compliance along all the directions, or programmed compliance along those directions. Rotational motions, it has all the constraints, it cannot rotate in any of the direction. So, what happens is a force guided motion along z is made to open or close the drawer. Motion is limited by the end stop forces along the z axis. So, as soon as it feels a jerk, when it reaches to its limit, it stops. Okay. So, what is the modifier here is external force, that is because of the, you do not know the straight line path with which you have to pull it out. Okay. So, you do not know that path, you can simply pull it out in any of the estimated direction. So, this force, basically these x and y forces which are generated out of the reaction forces will correct the trajectory. Okay. Because of the compliance, that trajectory gets corrected based on the reaction forces that are generated due to the positional error or the trajectory error. okay, and finally it is opened or closed. Okay. So, this is case 4, and the case 5 is opening and closing a hinged door. So, hinged door has an axis about which it can rotate. Okay. So, again in this case there is translational constraint along x, y and z. It like the earlier one had a rotational constraint in all the direction, this one has translational constraint in all the direction. It cannot translate in any direction. Okay. But yes, this point where the robot is actually interacting with the door, actually that is supposed to move in a xy plane. Okay. So, now rotational motion constraint is there along x and y direction. So, you cannot rotate about x, you cannot rotate about y, okay, can only rotate about z axis. So, the constraint forces guides the motion during opening and closing of the door. External force control or impedance control loop is used. Okay. Any small interaction forces that generate the reaction force are absorbed by the body during the motion. Body, it may be the robot or it may be the handle where there is some compliance or clearance. The input trajectory need not to be the arc which is shown here. So, you simply can move it in a straight line. So, the forces becomes the modifier to the input trajectory. So, input trajectory could be a straight line along this path, it could be a arc which is approximately in a xy plane. So, yes, in this case also end effector compliance or any clearance is very much helpful, and this is the way these type of tasks are done. Okay. Next one is pressing a button. Okay, pressing a button. So, again this is very much like writing on a board. You see, you have motion axis along x and y direction, and force you have to maintain a small force perpendicular to the button in order to press it. But to reach vertically above this button could be a vision guided. So, let us discuss the constraints here. It is translational constraint along z direction. Along this you cannot move, but yes, you can definitely lift it off the button. Force along z direction you can generate, and it is required. Free to move along x and y direction. Okay. Rotational constraint there is none, but yes, that is not advisable also. The robot in position mode reaches vertically above the button using some maybe a vision which is there, vision system which is there, which detects exactly the button which is to be pressed, and then you reach vertically above that. No orientation change is made after the tool aligns perpendicular to the plane. Again, this may be a vision guided, you detect 4 corners and detect perpendicular to this plane, okay, using some kind of marker which may be there, okay, and perpendicular to the plane you align your robot along that. Okay, you reach vertically above the button, go gradually downwards in force sensing mode along z direction. As soon as the contact is established, you apply a small amount of force based on the force sensor reading which is there. Okay. So, the robot starts moving in force sensing mode along z towards the button and stops upon finding the small force upon establishing the contact. Okay. So, this is how these tasks are performed. Okay. The next one is rotating a knob switch. How is this done? Again, you need to have an impedance controller or a external force control loop in case of standard industrial robot. This could be a cobot also. So, compliance and clearance definitely is going to help you here also. Translational constraint, you cannot translate. Once you have holded the knob, you cannot translate anymore. Force along z direction, that is required to establish the contact. Okay. Vision guidance is needed to get to the position where your knob is, how is your knob oriented, and establish yourself exactly above the knob. Rotational constraints you have along x and y direction, you cannot rotate. The robot in position mode reaches vertically above the knob. no orientation change is made after the tool aligns perpendicular to the plane. So, this is the plane I am talking about. So, you again may have markers normal to the surface is detected and robot is aligned exactly perpendicular to this surface before lowering to the surface. Okay, the robot starts moving in force sensing mode, okay, along Z towards the button and stops upon finding the small force upon establishing the contact. Okay, the knob is now rotated about Z axis until the sensor reads a small movement in clockwise or counterclockwise direction, whether switching it on and off. Okay. So, this is how these operations are done and these are the constraints. Okay. So, this is all about the constraints. So, to do day to day task which normally a cobot or a human does in its day to day life. Okay. Okay. So, these are the video I would use to demonstrate the features of a cobot, that is the capabilities of a cobot. Okay. So, this is a gravity compensation task. What is done here? I am able to drag the robot to any location, and this gravity compensation task here is essentially maintaining the orientation, but I am able to take it to any position x, y, z. Okay, so that is being done here. Okay, so it is fully free, it is gravity compensated. Active gravity compensation is there. Live sensors are giving the robot the feedback. The controller is continuously putting in the gravity compensation torque and it is able to do this. So, this is wonderful thing when you can do easy teaching. Full gravity compensation, you can even change the orientation you see. End effector orientation can also be changed. Okay, I am able to rotate, I am able to do roll and the pitch operation. I can drag it to any XYZ point. This is full gravity compensation. It becomes literally very difficult when everything is changed, and this is a redundant robot, so it has 7 degrees of freedom. I am actually taking it to a point which is to be taught. Okay, I took it there, I brought it back, so it may help me to teach that point. Okay, now it is with position control, so I can change the orientation, but position is controlled. You can do this also. This is again a gravity compensation example when orientation can change, but the position of the end effector or any point, any reference point can be kept stationary. So, I am able to move about that point, whole of the robot can move about that point. Got it? Now, Cartesian stiffness along xy plane, but it is free to move along x. So, along x direction, that is back and forth direction, I am able to pull or push this robot, but yes, in other directions it has stiffness. It may be set to some 100 Newton per meter or something like that. So, it is programmable stiffness that I can put in the task space. Again, it is along xy plane, free to move along z direction. So, again in x direction there is some stiffness, along z it is free, along y also I cannot move it, there is some stiffness. So, this is all Cartesian stiffness. Okay. So, these are some very special features which can let it do some special tasks. Now, it is free to move along x, y, z, stiffness are set to 0. So, this becomes very much like a gravity compensated with position controlled robot. It can be dragged to any place in 3D space. And now it is Cartesian stiffness along z, free to move along xy. So, I can take it on xy plane. but not definitely the vertical downward direction. Okay. So, these are multiple ways you can have compliance axis and the free axes. Okay. Okay. Then it is having Cartesian stiffness control, different values along each direction. So, this direction you see it is very less stiffness it has, other direction it is even less, but in vertical direction maybe it is having little higher one, you see. So, all the directions can have different stiffnesses again. Okay. Maybe you are handling some load in the vertical direction. So, this is orientation stiffness. So, about that point you can do, again you can have different stiffness, angular stiffness along each of the direction x, y and z. Okay. But it can maintain the position, see it is maintaining the position, but I can change the orientation about that position. Okay. This point can be changed as well. So, now it is at flange center, it can be arbitrary reference compliance also. Reference point is set at the flange center. I have just attached a tool so that you can observe it carefully. This time it is about the center of the flange that orientation is changing, and that point can be somewhere down below, somewhere else. So, it is at the tip of the tool, about that I am able to move it also. Okay. Again stiffnesses can be changed around each of the direction. This type of thing is very useful when you do any maybe a skin penetrated laparoscopy tool, you have inserted it, you want some point to remain stationary, you can put that point as a reference point. Force triggered stop, see initially it is moving downwards and it does not sense any force, I am hitting it. Okay. So, it is having no sense of force. Now, this time force triggered stop is activated. So, yes, as soon as I hit it, so you see it has stopped. It can be even started with a force, can stop with a force, you can stop with a force, start with a force. This is null space, this is a 7 degrees of freedom robot. When it has infinite solution to go to a place, like end effector pose is fixed, in between joint angles can change and even that stiffness can be adjusted. Okay. Stiffness is increased, I need little more amount of force to adjust that. It comes back to that. End effector stiffness is also there. This is selective programmable compliance, arbitrary surface following with force sensing you can do. So, yes, in this case a vertical downward force is maintained while I am giving motion along y direction. Okay. In one of the direction I am giving motion. So, it is maintaining the force, when it is elevating it simply comes up, it simply comes up. I am moving the table also, the profile is unknown for the robot, so it also follows that. So, unknown trajectory can be followed, you just maintain the force and move from one end to the other end, you can simply do this operation. Okay. So, I am moving the table in different orientation, still it is able to track the trajectory. Okay. The surface profile it is able to do it. So, maybe in a kind of grinding, polishing, buffing task, this can be very, very helpful. Okay. There are stiffnesses along x and y direction. Y direction I am moving, x there is a stiffness, z there is force maintaining. I can lift it because only 10 Newton I have set. Okay. So, this is these are few videos that you have seen: lead through programming, gravity compensation, Cartesian positioning, impedance control you have seen along each selected axis, arbitrary reference compliance, force triggered brake or motion can be done, null motion, and selective programmable compliance. So, these are some of the capabilities of a standard cobot which you should look for if you are looking for a good cobot. Okay, so yes, these control algorithms that goes behind we will be discussing later in our course also. So yes, for this lecture I will end here. In the next lecture we will start with cobot actuators, sensors and safe workspaces. Okay, that's all. Thanks a lot.